Assalamu alaikum. This is lecture number 7, Physics 731. In this lecture, I will give an expansion of a Green's function in spherical system of coordinates with some examples. In the previous lectures, we found that the expansion of Green's function for a free space 1 over x minus x prime is given by this expressions. This is the radial part and this is the spherical harmonics. Now let's apply this to solve the exterior problem of a grounded sphere. We solved this problem in a previous lectures or in the class. Now this is the coordinate for the source term where the charge is located, and this is for the field point, and this is the image. We found that the Green's function for this problem is given by this expression. Now we have to expand this in terms of this expression in terms of spherical harmonics. The first term is already this term. Now let's do the second term. Now we convert this to a square root of this formula, and then let u equal a square over x prime. Doing so, we get this expression. Now the denominator is nothing but this expression, but instead of r we have now u, which is a square over x prime. Now then substitute instead of u, we get the expression for this part in terms of the spherical harmonics. Now this is finally, by little algebra, one can reach to this expression. Now substitute this expression in the Green's function. We get this expression. This is the first term, which is 1 over x minus x prime, and this the second represent the second term, which is this term. Now let's check that this gives 0 at x equal a, because the sphere is at 0 potential. If we put x equal a or x equal or x prime equal a, we have to get the same result, and this result must be 0 because this function is symmetric in x and x prime. Now let's simplify this, break it into two expressions, one for r less than r prime and one for r greater than r prime, and then substitute for r a or for r prime a, we get this expression. Now this thing is 0 and this thing is 0. It means that g at x equal a is equal to 0. Now g is satisfied this differential equation. Now let's expand this in terms of the spherical harmonics by first writing the Dirac delta function in terms of the spherical harmonics. Let's write it as 1 over r square sine theta, this is the Jacobian, times delta r minus r prime times delta phi minus phi prime times delta theta minus theta prime. Now let's absorb the sign here in this expression and recognize that this is nothing but the completeness relation, which is the summation over Lm y Lm star of theta prime phi prime y Lm of theta and phi. Now we substitute this expression here, and for g we assume that it's some function of that depends on r prime theta prime phi prime times y Lm of theta and phi. Now we have this expression for this equation number 1. Now we have to operate on the on the right side by the Laplacian, which is the derivative with respect to the vector x. Now this is equal to the Laplacian of this term times y Lm plus this term times the Laplacian of this term. This is the expression I used. Now the Laplacian of this term, the Laplacian with respect to r at ylm can be written as in this expression, the red one, which is minus, it is easy to show that actually, it's minus L of L plus 1 over R square ylm of theta and phi. We substitute for this expression now, and we equate the right side of this equation with the left side to get this expression. Now we assume that ALM is some function, the reduced, we call it reduced Green's function in previous lecture, times YLM star of theta prime phi prime. Now the coefficient of this must equal to the radial part of the right hand side, which is minus 4 pi over r squared delta r minus r prime. So again, this is the differential equation for the reduced Green's function, which is g sub l r prime. The solution for this is well known to us, which is proportional r to linear combination of r to the power l and r to the power l plus 1. We have two expressions because r lesser than r prime or r greater than r prime. Now to find these constants a, b, c, d, let's take an example for that. Take two concentric spheres at zero potential. The inner sphere has radius a and the outer spherical shell has radius b. Now the Green's function at the surface of each sphere is 0, or the GL small, which is the reduced Green's function r prime is equal to 0 at r equal a and r equal b. We apply this to this expression. We get b in terms of a and we get c in terms of d. We get this expression. Now a and d are dummy variables. Let's change them to a and b as in this expression. Now to find a and b, we still have to use the properties of Green's function, which we did in the previous lecture. That is the continuity of g sub l at r equal r prime and the jump in the first derivative of g sub r prime. This is the continuity equation when r equal r prime, and this is the jump where we use the differential equation satisfied by g sub l. Now doing so, we get that g sub l is given by this expression and b by this expression using equation 1 in the previous slide and equation 2 and solve for a and b. We finally reach to this expression. This is Green's function, the reduced Green's function. The full Green's function now we have to multiply by ylm star of theta prime phi prime ylm of theta phi. So the final expression for g of x prime is given by this thing. It's a very long expression and we will use it in the next lecture inshallah. Thank you.